Hello and welcome. Today, we're going to break down one of the most fundamental components in electrical engineering, the transformer. We'll start with the basics by looking at an ideal transformer and then walk through the simple derivation of its voltage transformation ratio. By the end of this, you'll understand exactly how a transformer steps voltage up or down. Let's begin by looking at the diagram of an ideal transformer. At the heart of the system, we have the AC supply. AC, or alternating current, is crucial because transformers only work with a changing current. This changing current creates a changing magnetic field, which is the key to how a transformer operates. This supply provides the input voltage, which we call V1, and drives the input current, I1. This current flows into the primary winding. This is simply a coil of wire with a specific number of turns, which we label as N1. The primary winding is wrapped around a transformer core. In an ideal transformer, this core is made of a perfect magnetic material. Its job is to contain and guide all the magnetic field, or magnetic flux, created by the primary winding. This magnetic flux, represented by the symbol phi, and the dashed lines, travels through the core. Because the input current is alternating, this magnetic flux is constantly changing and reversing direction. This changing flux then passes through the secondary winding. This is the output coil, which has a different number of turns, labeled N2. As the changing magnetic flux cuts through this second coil, it induces a voltage in it, according to Faraday's law of induction. Finally, the secondary winding is connected to a load. This is the device or circuit that we want to power. The voltage across the load is the output voltage, V2, and the current it draws is the output current, I2. You'll also see E1 and E2 in the diagram. E1 is the electromotive force, or EMF, induced back into the primary coil, and E2 is the EMF induced in the secondary coil. These are the voltages generated by the changing magnetic flux. Now, let's move on to the derivation to see how these parts relate to each other mathematically. Step 1. Define the parts. First, let's clearly define our variables. V1, N1, and E1 represent the primary voltage, the number of turns in the primary coil, and the induced EMF in the primary coil. V2, N2, and E2 represent the secondary voltage, the number of turns in the secondary coil, and the induced EMF in the secondary coil. And phi represents the magnetic flux that links both coils. Step 2. Write the formula for each winding. The operation of a transformer is governed by Faraday's law of induction. This law states that the voltage, or EMF, induced in a coil is equal to the number of turns in that coil multiplied by the rate of change of the magnetic flux passing through it. So, for the primary coil, the induced voltage E1 is given by E1 equals N1 times d phi slash dt. We'll call this equation 1. Here, d phi slash dt represents the rate at which the magnetic flux is changing. Similarly, the same changing magnetic flux also passes through the secondary coil. So, the voltage E2 induced in the secondary coil is given by E2 equals N2 times d phi slash dt. We'll call this equation 2. Notice that the term d phi slash dt is the same in both equations. This is because, in an ideal transformer, all the flux created by the primary winding perfectly links with the secondary winding. There are no flux leakages. Step 3. Combine the equations. Now, we want to find a direct relationship between the voltages and the number of turns. The easiest way to do this is to divide equation 2 by equation 1. So, we have E2 divided by E1. On the other side of the equation, we have N2 times d phi slash dt, divided by N1 times d phi slash dt. As you can see, the flux term, d phi slash dt, appears in both the top and bottom of the fraction. This means it cancels out completely. This leaves us with a very simple and powerful relationship. E2 divided by E1 equals N2 divided by N1. This tells us that the ratio of the induced voltages is exactly the same as the ratio of the number of turns. Step 4, the final step for an ideal transformer. Now we make one final, important assumption for an ideal transformer. An ideal transformer has no losses. This means the wires in the windings have zero resistance. Because there is no resistance, the terminal voltage applied to the primary, V1, is exactly equal to the induced EMF, E1. So, V1 equals E1. Similarly, on the output side, the terminal voltage across the load, V2, is exactly equal to the EMF induced in the secondary winding, E2. So, V2 equals E2. Now, we can substitute V1 and V2 into the equation we just derived. Result, the voltage transformation ratio. By replacing E2 with V2 and E1 with V1, we arrive at our final result. V2 divided by V1 equals N2 divided by N1. This is the voltage transformation ratio, and it is the fundamental equation for an ideal transformer. It shows that you can control the output voltage simply by choosing the number of turns in the primary and secondary coils. If the number of secondary turns, N2, is greater than the primary turns, N1, the voltage will be increased, which is called a step-up transformer. If the number of secondary turns, N2, is less than the primary turns, N1, the voltage will be decreased, which is called a step-down transformer. And that's it. We have successfully derived the relationship that governs how a transformer works, starting from basic principles. While real-world transformers have some minor losses, this ideal model provides the essential foundation for understanding these incredibly important devices.